Oh, hi. Welcome to the room I've been hiding in Montreal for the last 15 months. It's bloody hot here. I just finished a tub of ice cream. The kids are in bed. Let's go. Good to go. First, big thank you to the organizers of the whole conference and this session. It's shaping up to be a pretty good one. There are going to be points in the video where it might be appropriate to pause it. I'll indicate that by going like this. Maybe you can pause it and have a think about what you want to do. Well, think about whatever's going on and then continue when you're ready. So, there are two goals to this talk. One of them is to convince you that infinite type surfaces are worth thinking about. So if you're someone who's outside this area and you just wandered in off the street into one of these talks, they're worth thinking about, and failing that they're fun to think about. All right. So before we get started on the actual mathematics, everything I talk about today is joined with Alan and Federica. There they are. So here's the spoilers if you don't want to stick around for the rest of the talk, if you're already bored. We're going to use homeomorphic subsurfaces to construct nice graphs on which mapping class groups act. That's the goal of the talk. How we're going to do that is first I'm going to talk a little bit about the classification of surfaces, and then we'll talk about homeomorphic subsurfaces, omnipresent arcs, and stable surfaces, which will set up the groundwork for the main theorem. Here we go. So first, let's start off with the important question. Why should you care about infinite type surfaces? Well, first, if you run into one on the street, you should expect it to be infinite types. If you run into a surface in nature, there's no reason to expect the fundamental group to be finitely generated. That should be a special case. Infinite type surfaces ought to be generic. We should be thinking about them. Miraculously, there's a classification. Classification theorems are super useful in mathematics, right? They're incredibly powerful. A good classification theorem you tend to use without thinking about. For example, if you know you have a threefold cover of a genus 2 surface, you know it's a genus 4 surface immediately. Right? This is kind of remarkable that you can just say that without even thinking that you're using this amazing classification theorem. And to refer you to Marissa's introductory talk to big mapping class groups, they're totally worth thinking about. I won't say too much there because she does a much better job than I could do. So have a look if you want to be convinced about big mapping class groups. All right. So in order to talk about the classification of infinite type surfaces, which is the first thing I want to do, we have to talk about the ends of a surface. So an end, intuitively, I'm not going to define it formally, but it's a way out to infinity. So let's have a look at this picture here. This is an infinite cylinder. And then to the left here, you've got a bunch of punctures. So throughout this talk, any black marks, any black dots on a surface will be a puncture. Right, these are punctures going out all the way to infinity to the left, and to the right, you've got genus going all the way out to infinity. All of these are ends. So each of the puncture is an end. It's a way out to infinity. You can think of like a puncture as a cusp if you want, if you don't like the puncture going to infinity. And if I go out to the left, that's going out to infinity, or I can go out to the right. That's going out to infinity. All the ends form a set. Some ends are different. Some are accumulated by genus, which means as you keep going out to infinity, you keep seeing genus. The end to the left, let's say you start over here and then start moving to the left. Eventually, you get to a point where you no longer see genus. So that's a planar end. But if you keep seeing genus, that's an end accumulated by genus. And they form a subset of the end space, naturally. Great. You can topologize the space of ends, right? And the way you're going to do it is you're going to say two ends are in the same open set if they belong to the same subsurface with compact boundary. Okay, so that's the verbal definition, but let's just do a bunch of examples to get used to it. So here's the same surface that we just talked about. All right. The end space, which we're going to think of as a topological pair, is a bunch of isolated ends, which are these punctures, and they all accumulate to the big end on the left. All right. And the one on the right is just an isolated end, but it's accumulated by genus. So we're going to draw that as a red dot. So here's what the end space looks like. It's a bunch of isolated ends accumulating to an end, and an isolated end that's an end accumulated by genus. What about this one? This is the ladder surface. This has two ends, and they're both accumulated by genus. So genus goes out in both directions. Two ends, two isolated points, both accumulated by genus. So the topological pair looks like this. Here's the Loch Ness Monster. Terrible name. Anyway, we're here. One end, it's accumulated by genus. The end space looks like this. What about this? What if we take the ladder and we puncture every rung, right? So then these isolated planar ends, they accumulate to the two big ends on either side, and each of those ends is accumulated by genus. So that's what we see here, right? You've got these isolated ends accumulating to the two ends accumulated by genus, right? So the red ones are a subset of all of them, but like this is sort of how they sit inside the end space. You could take a sphere and subtract the Cantor set, which is what we've done here. That's my artist's impression of a Cantor set. And because there's some kind of justice in the world, the end space is indeed homeomorphic to the Cantor set. Or you could take an infinite binary tree and blow it up and look at the sort of boundary of what ends up happening. And this is a perfectly good surface. And the end space of this is the Cantor set. It's a fun little exercise to try and identify your favorite version of the Cantor set with these ends. Or you could put genus at every vertex and you end up with the blooming Cantor tree, and the end space is a Cantor set, but this time every end is accumulated by genus. Or what about this guy? So this one is you take the plane and at every integer lattice point, you glue in a handle. It turns out that this surface only has one end and it's accumulated by genus. So one end out at infinity. So this one's a little weirder, but it's true. So here are some fun facts about the space of ends. It's homeomorphic to a closed subset of the Cantor set. Right? The Cantor set has being a closed subset of the Cantor set is equivalent to like being Hausdorff, compact, totally disconnected. I might have the adjectives wrong, but there's a universal property. You check those things and you conclude that you're homeomorphic to a closed subset of the Cantor set. And the ends accumulated by genus is a closed subset of that. So if you have a surface, you have this topological pair, which is a closed subset of the Cantor set and a closed subset of that. Here's the amazing classification theorem, is that data, along with the genus, is enough to classify your surface. Okay. So the theorem says the homeomorphism type is entirely determined by the genus and the homeomorphism type of the topological pair, end space with the ends accumulated by genus. Even better, if you give me some data that could potentially be realized by a surface, it is realized by a surface. This is kind of remarkable. The only thing you got to be careful of is that the genus, if the genus is finite, there can't be any ends accumulated by genus. And if there is an end accumulated by genus, the genus has to be infinite. Cool. So the classification theorem tells us that the sphere minus the Cantor set and this Cantor tree are the same. Or it tells us that these two surfaces are the same. Cool. Right, classification theorems are powerful. You should use them. They're awesome. All right. So let's talk about mapping class groups. If you want to study big mapping class groups, or let's study small ones first. So mapping class groups of finite type surfaces. If you want to study a mapping class group of a finite type surface, one tool you have is the action of the mapping class group on something called the curve graph. So what's a curve graph? It's a graph you associate to a surface where the edges are just isotopic classes of simple closed curves, and adjacency is given by disjointness. So here I've drawn a subgraph of the curve graph of this surface. This blue curve can be realized disjointly from this red curve, pink, and green. So the blue has an edge joining all of them. The pink one cannot be realized disjointly, cannot be isotoped to be disjoint from the red or green. So there's no edge between the pink and red and the pink and green. So you take all the curves on the surface and you ask, and you join them up according to these rules, and then you look at that graph. Right? The mapping class group acts on this because it preserves, it sends curves to curves, and it preserves disjointness. And here's an amazing theorem, is that the mapping class group, if you allow orientation reversing homeomorphisms, is actually isomorphic to the automorphism group of the curve graph, at like graph automorphisms. That's not all though. Here's what's really amazing, is that as long as you're not one of a few sporadic cases, the curve graph of a finite type surface is infinite diameter and delta hyperbolic. Right, so suddenly you have this delta hyperbolic space on which your mapping class group acts, and you can suddenly start proving theorems, because that's what geometric group theory is all about. The mapping class group is relatively hyperbolic, for example. You can identify pseudo-anosovs by asking which mapping class groups induce hyperbolic isometries on this hyperbolic space. It's just like such a wonderful picture to have all together. You can use the delta hyperbolicity of the curve graph to give you quasimorphisms mapping class group, and this is just some of the applications of this theorem. Anyway, super powerful, ultra powerful. What about for infinite type surfaces? What goes on with the curve graph? Well, exercise. The curve graph of any infinite type surface has diameter 2. This is where you boo and you throw tomatoes and you're like, let's go home, let's just give up. Or you can be a responsible mathematician and ask the following question. Is there some other kind of graph we can associate to our surface which is good, right? Which gives us like delta hyperbolicity and the mapping class group acts nicely on it and it's infinite diameter. Right? Can we construct a nice graph? That's the goal here. So the answer for some cases, what's known before we came along, is yes. So the whole sort of a lot of interest in big mapping class groups came from this paper of Juliette Pavard, which is part of a thesis. And she showed that the ray graph on the plane minus a Cantor set, which is a particular kind of graph you can associate to like rays on your surface, is delta hyperbolic infinite diameter. The mapping class group acts nicely on it. Blah, blah, everything you want, right? It's just like such a beautiful picture for this particular surface. So R2 minus a Cantor set, you can think of the end space as an isolated end and a Cantor set. And rays are just embedded copies of R that start at the isolated end and end at one of the punctures. Okay, and you construct the graph the same way you do the curve graph. So disjointness gives you adjacency. And then this was generalized for any surface with a single isolated planar end, so a single puncture. You look at the ray graph on that. Or you can look at the arc graph on a surface with finitely many isolated planar ends, so finitely many punctures, and you look at arcs which go from one puncture to another. Or for a larger class of surfaces, you can construct something called a two-separating curve graph. And this is delta hyperbolic infinite diameter. And the mapping class group acts nicely on it. So this is actually a subgraph. So all of these three are ray graphs. So they're like built out of arcs. This one's actually a subgraph of the curve graph. But you have to choose which curves you want to pay attention to, and then everything works out fine, which is great. So these are all beautiful, and they require sort of choices. They say, we're going to look at only these arcs or only these surfaces or only these curves. And they're really great, like clever choices and things like this. All right, so what did we do? Well, we came at it from the point of view of homeomorphic subsurfaces. What's a homeomorphic subsurface? Well, it's what it sounds like. It's a subsurface which is homeomorphic. Now, if you're a finite type surface, Euler characteristic arguments can show that there are no sort of interesting subsurfaces that are homeomorphic to the whole thing. Right? If you have a genus 2 surface, you can't, any subsurface which isn't the whole thing, has genus 1, or maybe it's like missing a couple of boundary components or something, and you can show that is never going to be homeomorphic to a genus 2 surface. However, in the infinite type setting, this can happen. You can actually have like proper homeomorphic subsurfaces, and that's what we're going to study. So how do we build these? So we build them out of loops. So what's a loop? It's an embedding of the real line that starts and ends at the same end. So it starts at infinity somewhere, it goes into your surface, and it goes back out the same way. And such a loop is separating if when you cut along it, or you delete it, you're left with two components. And the homeomorphic subsurfaces that we're going to be interested in are exactly ones built this way, where you take a loop, you look at the two components, and one of them has to be homeomorphic to what you started with. Okay, and it can't be homeomorphic in a silly way. It has to actually like miss some topology. The stuff that you delete has to have some topology. So that's what we mean by a proper homeomorphic subsurface. Let's do an example. Here is the Loch Ness Monster, and here is a loop. In fact, it's a separating loop. It separates it into this and this surface gamma. You can use the classification of surfaces or anything else you want to show that gamma is actually, if you just delete alpha, So we're not closing up. We don't get any boundary or anything, right? We're just literally just deleting alpha. Then what's left over has one end and infinite genus, so it has to be the Loch Ness Monster again. And this is kind of cool. You've got this loop that comes in and sort of, while the surface isn't looking, it takes away some of the topology, and then the surface doesn't even notice, right? Just lobotomizes a bit of the surface of, and everything's fine. Successful lobotomy. All right. So here's the first theorem: is that having one cut homeomorphic subsurfaces is a characterization of being an infinite type surface. And here's just a quick sketch of the proof by examples, not the one that's in the paper, but a proof. Here's the Loch Ness Monster, except spread out over the plane. Here's a loop, alpha, which starts and ends at the same point at infinity, right? The same end, because there's only one end here. And if you just look at the upper half plane, if you will, that's again a Loch Ness Monster. And below you've got some topology, so it's actually a proper homeomorphic subsurface. Great. What about some other surfaces? What about like the ladder? Well, here's the ladder. Use the same arc. An exercise is to turn every surface, every infinite type surface, into a picture like this, where you've got sort of the same thing at every integer coordinate, except for one point where you can put whatever you want. And then you just cut out what's below alpha. And you have a one-cut homeomorphic subsurface. Cool. So, as the old saying goes, when life hands you homeomorphic subsurfaces, you create an arc graph. So that's what we're going to do. So, how do we build our arcs? So an arc is an embedding of the real line with two different endpoints, right? So it starts somewhere, it goes in, and it goes out somewhere else. And we say an arc is omnipresent if it intersects every one-cut homeomorphic subsurface. I find it easier to think of what not omnipresent means. Not omnipresent means that you're in the complement of some one-cut homeomorphic subsurface, right? So that means there's a loop which can kind of go around you and suck you away without the surface noticing. And then what's remaining is still a copy of the surface. That's what it means not to be omnipresent, right? So it's kind of like the arcs the surface doesn't even notice is gone, right? Whereas the omnipresent ones, you can't cut them away by this sort of one-cut homeomorphic subsurface business. All right, so let's do some examples. Is this omnipresent? Pause it, have a think about it. No, because I can draw this blue loop, and the complement of this blue loop on the outside is actually homeomorphic to the surface we started with, right? The surface we started with is like it has three big prongs, and then there's punctures going out in all three directions. No genus. All right, what about this one? Pause it, have a think. It is not omnipresent. You can sort of go out to infinity and then turn around and come back, and what's on the outside here is still homeomorphic to what you started with. What about this one? It is omnipresent. Exercise, prove it. This is cool. All right. So let's build an arc graph out of these omnipresent arcs. By the way, we initially called these things surviving arcs, and then casualties, and then the pandemic hit, and we were like, we better not use those words. God. Anyway, so omnipresent arc graph. How do we do this? Well, you just take, instead of looking at all the arcs, let's just look at the omnipresent ones. So the ones the surface is like, can't live without. Right? Let's just look at the omnipresent arcs. And then create an arc graph out of them in the usual way. Vertices are isotopy classes of such arcs. Edges is given by disjointness. So what's important here is that the surface is telling us which ones are important. We're not saying we want to only look at the arcs between these ends, or we only want to look at this or these surfaces. We're just saying, okay, you tell us which arcs are important to you, and we're going to deal with those, right? So the surface chooses, we're just listening. That's the important thing to take away here. This is sort of morally something we were really hoping to get out of this construction. So here's a special case of the theorem that we can prove. Let's have a look at this particular surface, which has 5 sort of big prongs. In these 3 prongs, you have ladders going out. This one, you just have isolated punctures going out to this big end, and then this big end, you have genus and isolated punctures going out that way. For this particular surface, here's what we can prove: that an arc is omnipresent if and only if it starts and ends at one of the five big ends. It starts and ends at one of the five big ends. So if you have an arc that starts out here and then comes in and then goes and ends up at the top of this ladder, there's going to be a way to cut that one away without the surface noticing. Even better, we can prove that in this case, for this surface and a bunch of other surfaces, but here's an example, that the omnipresent arc graph is connected, infinite diameter, and delta hyperbolic. Yes. Right, so this is sort of like really encouraging because we just chose what looks to be a random surface and we can get the results we want. Right. So at this point, we started getting pretty excited and going, oh, maybe we can do this for every surface. Wouldn't that be great? And then this surface, which is just like the stuff nightmares are made of, comes along. What is it? So take a big, take like a tube capped off at one end, an infinite tube, and then cut out discs, countably many discs going from one end, starting here and then going out to infinity. On the first disc, glue in a ladder. Second disc, glue in a ladder accumulated by isolated punctures. Third disc, glue in a ladder accumulated by punctures which are accumulated by isolated punctures. Fourth disc, glue in a ladder accumulated by punctures which are accumulated by punctures which are accumulated by isolated punctures. So on and so forth. And then you're like, oh man, just sent shivers down his spine. It's a nightmare surface. Here's what we can prove. For this surface, an arc is omnipresent if and only if both its endpoints are not planar. So if you start up here and go out to infinity to the right, that's going to be an omnipresent arc. Or if you start up here and then go and end up there, that's going to be omnipresent. But if you start at any of these punctures, you're not going to be omnipresent. Unfortunately, in this case, the arc graph has diameter 2. So we can't deal with surfaces like this. But it raises a natural question, like what's special about the other one? And what's special is this notion of stability. So this was arrived at by us and by Katie Mann and Kazmi Rafi sort of independently. And then luckily we talked to each other before our papers went out. So we agreed on the notation. So what's the idea of a stable end? A stable end is one that looks the same as you go out to infinity. It keeps looking the same. The scenery doesn't change. So it's kind of like in The Simpsons when they're walking down the street and the same clouds and same trees just keep going by on loop, right? And they just keep walking. That's what a stable end is, right? So, and a surface is stable if all its ends are stable. And just a bit more terminology, a finite order end is an end with finite mapping class group orbit. Finite order end. I think I should be writing finite orbit end. Finite order end. So here are some fun facts. If your end space is countable and you're all the ends are genus or planar, then your surface is stable. So this immediately gives you uncountably many stable surfaces. So there's a lot of them. Might not be all of them, but I mean, it's definitely not all of them, but there's a lot of them. And a stable surface has finitely many finite orbit ends. This is an exercise in compactness, but it's true. If you have infinitely many finite orbit ends, they accumulate to an end which is not stable. You can show this. So if you're handed a stable surface, it comes with finitely many important ends, the finite ordered ends. This surface is stable. This is the one we could prove all those nice results for. And these 5 big ends are the 5 finite orbit ends in this case, finite order ends. This is not stable. Every end is stable here except for the one out to the right. If you keep walking out to the right, the scenery keeps changing. It never sort of stabilizes. So here's the main result. Suppose I hand you a stable surface. It has n finite order ends. We can prove that an arc is omnipresent if and only if both its endpoints are those finite order ends. And so a complete classification of the omnipresent arcs. And even better, if you have at least 3 of these special ends, then the omnipresent arc graph is connected, infinite diameter, and delta hyperbolic. Right, and this is nice because the surfaces that this covers gives a whole family of new surfaces that weren't covered by the other arcs and curve graphs in the literature at the time. So we actually got a whole bunch of new results here, which is great, which we're super happy with. So I'm out of time. So I will skip these, and if you're interested in some of the proof techniques, we can talk about it in office hours or anything like that. Thank you for listening. I will see you later.